Okay, first I'd like to thank Dylan and Riley and everybody else for making this happen. Just seeing everybody this morning brings back really good memories of last year, so thank you. And today's talk you can think of as an attempt here to take all the stuff that Antonetta was just talking about, taking these sea surface temperature events and turning them into bottom temperature events, and actually a mechanism for turning this into temperature anomalies at depths in the fjords and inlets of British Columbia. Oops, wrong computer. Okay, everybody look at this. I'm trying to make sense here of 3 generations of ocean temperature observing technology. The lighthouses in BC, we have 12 stations with records going back 80 and 90 years. This is where a guy walks down to the beach every day with a bucket, puts it in the ocean, measures the temperature. Subsurface moorings. And then what I still think of as new technology, although it's 30 or 40 years old, satellite sea surface temperature. So I'm going to try and reconcile these 3 different ways of measuring temperature in the ocean. The questions we're going to ask is, one, are there times of the year when we can use satellite SST to map bottom temperature? And then can we use coastal SST measured at these lighthouses as a proxy for bottom temperature and thus infer trends? Because one of the features of the Northeast Pacific, with all the decadal variability, records of 30 and 40 years long are not very useful for actually determining long-term trends. Here's the west coast of Canada, British Columbia. The blue are the lighthouses, where I say there's some of those records go back 70 to 90 years. And there we go. And then the red dots are places where we maintain subsurface moorings with some semblance of trying to be monitoring. Down here off Vancouver Island, Rick Thompson has maintained these 3 moorings there for the order of 30 years. And then as we go further north here, my own personal stuff, where we've had moorings, these 3 moorings here for the last 4 years. And then as we work our way up the coast, the records get a little shorter. But we're going to try and use this subsurface temperature data to look at how it relates to sea surface temperature. So we're going to just look at a set of time series at this location here on the north coast of British Columbia. So here's a temperature record, subsurface temperature records running from July to July of 2015 through 2016. The black is the SST from the NOAA data product. The blue is the 12-meter temperatures. The red is at 36 meters. The green is at 125 meters. And the water depth here is about 130 meters. So I take the green to be a measure of bottom temperature. And you can see the feature here is through August and September and October, the sea surface temperature decreases. We've obviously got, instead of increasing storms here, doing some mixing, because you can actually see the temperature at depth at 36 meters is actually increasing while the surface is decreasing. And then once the temperatures in the upper 40 meters meet, then they all decline while the bottom temperatures are actually increasing until they all meet sometime in December. And then for a couple of months, there's really, the water column was actually quite isothermal. So for fun there, you'll actually notice that the maximum temperature at 40 meters is in November, not in the summer. The other interesting feature here, which I won't show, is that the salinity, the water column remains stratified in salinity, certainly on monthly timescales. So what we're going to do is we're going to exploit the fact that the temperatures are all pretty much the same through January and such, and have a look at January temperatures. So first I'm going to look at these mooring locations, where the blue guy, I have 3 years of measurements, and the reds, I've got something, records of various lengths starting in 2016. So you take all the moored temperature measurements there, gives you this set of dots. And you can see that there is a general trend, but there's a set of points that are kind of weird. Those are all the measurements that are deeper than 150 meters. So we're going to throw them out. And we're going to look at all the stuff above 150 meters. You do that. Oh, right. And here in the green, there's those 2 green dots there pointed out by the green arrow is actually where the time series that I showed you. You can see I actually managed to pick the time period when it was actually pretty much isothermal. You can see another set of green dots there, where they're another year where they're a little more separated. And then there's a set of green dots in the lower left corner where there's about a half a degree between the 47-meter guy and the 122-meter guy. And that's actually a year when the this isothermal, this mixing only reached to about 100 meters, didn't actually get down to 122 meters. So there's certainly some interannual variability to account for. So if you just take all that data, throw out the stuff deeper than 150 meters and just do a linear regression, you get a really amazingly good good result. You know, the p-values are ridiculously small. Slope is one, you would like a 1-to-1 slope, which is the orange line. What you get is the blue line, the slope of 1.16, but it turns out it's actually not different from 1 at 95% confidence, and the intercept is not different from 0 at 95% confidence. So for the data we have on the North Coast, it looks like you actually can use satellite SST as a measure of bottom temperature down to something like 100 meters in the month of January. We now move to the west coast of Vancouver Island, where we have much longer time series, start to account for some of the interannual variability. Do the same thing. We've got those 3 records. If you just plot at all the January monthly means at all the locations and compare it with the satellite SST across the bottom. And once again, we got a series of points that don't seem to fit the general trends. And those magenta guys are the values at A1 at 100 meters, which is the mooring at the edge of the shelf. The other 2 moorings, EO1 and BP1, are actually are sort of in the near coastal zone, about 100 meters of water or so. But it's clear that A1 doesn't want to conform to my ideas. So we're going to do the same thing. We're going to run the regressions, but we're going to exclude A1 at 100 meters. We get this. I will point out that here, this is certainly a non-trivial data exercise, as I actually have 100 estimates of January monthly mean temperatures. There's a lot of mooring data. The slope is 0.85. Once again, a person would like a 1-to-1 slope, but we don't get it. And we get a fairly substantial intercept. And because there's lots of data, the slope and the intercepts are different from 0 at 95% confidence. So the relationship on the Vancouver Island shelf is not, you don't get a nice 1-to-1 slope, but it still has a potential use as a proxy. The standard error of this regression is about 0.3 degrees C, which I take as a fairly small error, given that I'm basically trying to use sea surface temperature as a metric for temperature at 75 or 100 meters depth. So the first question is, can we use satellite SST as a proxy for January bottom temperature? And the answer is yes. On the North Coast, possibly down to 100, maybe as much as 150 meters. The Vancouver Island shelf, down to 75 or 100 meters. And to do that, you sort of have to accept that you're going to have errors of the order of a half a degree. So here I've got satellite imagery for January 2014 and January 2015. So 2015 is when the blob comes ashore. And the red areas I got circled in red, are kind of areas that are typically less than 100 meters deep. And you can see there's about 2 degree temperature difference. So I think that's real, and that's actually a measure of the changes in bottom temperature in the month of between the 2 Januaries. So we got about a 2 degree temperature anomaly due to the blob in January 2015. 2 degree bottom temperature anomaly due to the blob. Okay, now I want to go chasing proxies. I'd like to look at long time series. So we're going to focus on EO1 in the middle of the Vancouver Island shelf there, and we're going to compare it with data from Amphitrite Lighthouse, which is where the guy goes down with a bucket once a day to measure the temperature. And we're also going to look at the relationship with air temperature, which is the green dot there. So 3 locations reasonably close together, and see how well they correlate. And the reason for wanting to chase these proxies is shown here. So the red is the data, the monthly mean, January monthly means at EO1. And you can see that they go back basically to the early 1990s. There's one data point in the 1980s. So it gives you 30 years record, which is about the same as the satellite SST record. Whereas the air temperature and the coastal sea surface temperature go back much, much longer, back into the 20s. And so it would be nice to be able to use those long records as proxies for our bottom temperature. So here's the correlation between the satellite SST and the subsurface temperature at EO1 at 75 meters. So we're ignoring all the other temperatures we got, just going to do time series analysis at this one location. And it's actually quite good. The slope here is 0.86, which is about the same slope that we got when we did all the data together. P-values are ridiculously small. The residuals, again, are about 0.3 degrees Celsius. And there's 29 data points. So we can certainly use the satellite SST to gap fill the EO1 temperatures at 75 meters. That would allow us to have a continuous time series for the length of the satellite record. We now look at the relationship between the subsurface temperatures at EO1 at 75 meters and the coastal SST. This is what we get. We get about the same slope again. We get really good regression statistics with P very, very small. Standard deviations of the residuals now become a little larger. They're now 0.6 degrees C. So it's credible to actually use this as a proxy. Not going to be perfect, but as a proxy for bottom temperatures. We now go look at the air temperature. We actually get about the same result using the air temperature as a proxy for the subsurface temperature. We actually get about the same result as we did using the coastal SST. So we really do, in January, we really do have a coupled system here where the air temperature, the sea surface temperature, and the temperatures down to 75 meters are all really tightly coupled. Knowing one gives you a lot of information about the others, which I think is kind of cool. And then if we go back, we can also use the air temperature as a proxy for coastal temperature, just sort of showing that the whole system really is coupled. Everything is tied together in the winter. So what are we missing here? We look at the residuals. I've got here the residuals both using the coastal SST as a proxy and using the satellite data as a proxy. And it's interesting that 2014 and 2015, the proxies have fairly large residuals in opposite directions. There's something really interesting going on in 1998. So there's clearly some work to be done here to understand why these particular years are the large outliers, and maybe we can actually improve our proxy things by understanding what's going on here. Maybe there's another variable we can introduce to improve our ability to predict to hindcast the bottom temperatures at EO1. There's probably also some information in when the residuals from the satellite are different from the residuals at from the coastal SST. There's probably some information in there as well that I haven't quite figured out what it means. So now we use the coastal SST and the air temperatures as proxies to then project the bottom temperature at EO1 back for the better part of 100 years. Those are the results that are shown here. You use those to compute trends. Turns out the trends based on the air temperature and on the coastal sea surface temperature are about the same. And you'll note that they are statistically significant. Turns out they're not enormously different from zero. They are, fortunately, we can say we understand, we do know the sense, the sign of the trend. But even with 100 years of data, with all the variability that we've got, finding trends in this area of the world is really difficult. And you'll notice that the bottom line there is the trend if you just use the 30 years of measurements that we've got at 75 meters. And you get a trend that's a little bit larger, but you get an enormous error that you actually don't even know with any confidence the sense whether the trend is positive or negative. So you really do, if you're going to talk about trends and other long-term variability in this part of the world, you really need these long time series. So the conclusion here is, yes, it is feasible to use the long records of coastal SST as proxies for bottom temperature in January. certainly down to depths of 75 to 100 meters, possibly deeper on the north coast. You can only do this if you can live with uncertainties of the order of a half a degree to a degree, which then suggests you're sort of into a 3-level classification scheme. If we just take the Amphitrite lighthouse data and we just break the data up into those years where the anomalies, where the temperatures, bottom temperature is half a degree above the mean, and those that are, that's red, those that are blue are half a degree below the mean, and the green are the stuff between plus or minus half a degree. So that's what I mean by a 3-level classification scheme. And if you stare at it, I haven't actually done any serious analysis here, but if you stare at it, you can see at various times I've tried to argue that we're not actually seeing an increase in the high temperatures, the high monthly means, but yesterday I changed the line a little bit, so maybe we are seeing an increase there. But what we have lost are the cold temperatures. And this is likely just due to the fact that over the course of this record, there's a 0.6 degree increase in temperature, and I set my bands at a half a degree, so we've sort of lost the lower band. And so I think biologically that has to mean something, that we no longer get the same cold winters at depth. But I haven't yet found the right person to turn this into anything useful. Okay, my summary here. So yes, we can use satellite surface temperature as a proxy for temperatures down to 75 or 150 meters in January on the north coast, and probably down to about 100 meters on the Vancouver Island shelf. I think it will eventually show that in January, the Vancouver Island shelf is still more highly stratified than the north coast. So this fall and winter mixing provides a mechanism for getting SST anomalies like the blob into the deep waters of the coastal fjords and inlets. So this actually links sort of the atmospheric deep convection over New Guinea all the way through marine heat waves like the blob into effects at depth in the coastal inlets. This process is not quite as simple as mixed layer dynamics, as the water column actually remains stratified by salinity on monthly timescales. And I have arm-waving arguments about how you manage to be isothermal in temperature and actually well mixed in oxygen, but not in salinity, but that's for another time. And there is potential to use the coastal SST and possibly even air temperature as proxies for longer-term analysis. And it may be that what we're capturing here are the sort of large-scale signals, those that are related to the sort of climate scale things and the other large-scale processes, and not so much the local up-close stuff. So I've run through that fairly quickly, and I thought I'd actually take this opportunity to update my talk from last year. The things that I've learned this year is that satellite SST in the Northeast Pacific is really an interesting thing. If you actually sit at a particular pixel and ask how often do you get a daily value, the answer is about 10% of the time. So these nice NOAA products, daily gap-free images aren't what you think they are. And in particular, the one that we've been using, the optimum interpolated sea surface temperature product, is constructed by combining satellite, ships, and buoys, and therefore it's not independent of the weather buoy data. You actually need to use a satellite-only data product to check on the data buoys. And the reason that this matters is last year I made a big deal about a potential marine heat wave in the northern part of Hecate Strait. And it turns out this is strictly an artifact of bad in situ data, because you only get measurements up there 10% of the time. It relies heavily on the in situ data, and if the in situ data goes bad, then you get a bad data product. With that, I will end.
Awesome. Exactly on time. Perfect.
Excellent.
Yeah. Thank you, Antonio.